Recording. Hi, folks. Welcome to Chapter 6, Lecture 7. And this is the last lecture in this Chapter 6 and the 24th in our series. I'll be talking today about the breakdown in solid and liquid dielectrics. In fact, we did talk about it. We started yesterday about it. The breakdown in strength of solid and liquid dielectrics is very, very high. Very, very high. So, unlike the gaseous dielectrics, so the measurement procedures, definitions, and the details are entirely different as compared to the gaseous dielectrics. In fact, air is very widely used, most widely used dielectric, but it is a poor dielectric in the sense it has very poor electric strength. So when we go to the solids and liquids, there are two types of strengths defined. One is intrinsic strength. Intrinsic means the inherent, which is very, very high. And then another one is the practical strength. When you measure under practical conditions, the measured strengths are much lower. And intrinsic strengths have to be measured under very high care. People try to estimate theoretically, and theoretically, very high values were estimated for intrinsic strength, especially in the case of liquid dielectrics. So, when you read this here, what is written, the most likely elementary process of ionization in hydrocarbon liquids is by excitation or molecular vibration, which is equivalent to thermal vibrations. As the physicists put it, the thermal energy, you may be knowing about the molecules. The process of dissociation of molecules in neutral, low molecular gaseous particles takes place due to severe molecular vibrations, which requires energy level of the molecule in the range of 1.5 to 7 electron volt. This is the process takes place in the dissociation molecules, neutral, low molecular gaseous particles. This is the energy required. Excitation of metastables, which may lead to ionization in a few stages, requires energy levels of the order of 1.5 to 10 electron volt. Higher energy level is required by metastables. And the scintillation electrons accompanied with weak luminescence, indicating high energy quanta of several electron volt, which is greater than 10 electron volt in some liquids, and to ionize the process. It is greater than, it is much higher. The scintillation of electrons in case of liquid dielectrics is much higher. And this is because the when we go back here, the mean free path of molecules, the ions, you can say, is to the order of, in liquid dielectrics, of the order of 10 to the power of minus 6 centimeter. And on the contrary, the basic process of excitation of molecules may lead to ionization in oils at uh, at no, so not contrary. I mean, with this mean free path and the energy of the ions, you can say, which lead to ionization. See, you cannot have breakdown without ionization. It's the question: what makes the ionization? What material makes the? What is the structure? What is the status of the molecule which makes ionization? In case of gaseous dielectrics, the ionization process is because of the kinetic energy of the electrons. Unlike there, in case of liquid dielectrics, the ionization process is with ions, you can say. And with this high energy level of 10 electron volt and mean free path of the mass and mean free path of the ions, which is slow, heavier, being 10 to the power minus 6, there has been theoretical estimation of the breakdown field intensity required in liquid dielectrics. And theoretically estimated estimation goes to something like 10,000 kV per centimeter. Can you imagine? 10,000 kV per centimeters for liquid dielectrics. But it is too high. It is just not possible. People have tried to measure it also. Then on the contrary, the basic process of excitation of molecules may lead to ionization at 200 to 400 kV itself. So that estimation made earlier of 10,000 kV per centimeter was wrong. It was a purely theoretical estimation and theoretical figures. But later people could measure, could estimate to the tune of 200 to 400 kV per centimeter, the field intensity of this order. Yeah, so this is not partial. Let me tell you, this is wrong here. You correct it. This is practical, actually. Practical breakdown strength of liquid dielectrics. I mean, you don't measure the breakdown strength of partial breakdown at the PB. You don't measure. You do make measurements of partial breakdown in liquid dielectrics, but this we are talking about the practical breakdown strength. So what we discussed just now was the theoretical value and very high values of the order of 10,000 kV per centimeter, but the people who measured something like 200 to 400 kV per centimeter. It remained within this limits. So the practical breakdown strength of insulating liquids is measured with the help of standard electrodes having weakly non-uniform field configuration. As you see here, in this figure below, figure A, this is the cross section and dimensions shown of the standard electrodes, which the two electrodes against each other, as you can see on the right side, the actual electrodes in a container where the practical breakdown strength is measured. And these are standard, known as standard measuring electrodes, known as calots. And these have been standardized and are widely used all over the world. So yeah, what type of field would this type of electrode, for a small gap distance, the gap distance kept for measurement is also standardized of 2.5 millimeter. 2.5 millimeter, that is one quarter of a centimeter, you can say. So what kind of field will be present in between the two electrodes? Nothing but a weakly non-uniform field configuration. And as you know, the major properties of dielectrics in uniform and weakly non-uniform field configurations are similar. So this BIS, the Bureau of Indian Standard, recommends the electrodes to be made out of brass with a good surface finish, whereas VDE, the German standard, recommends copper as electrode material. The electrodes are placed in a container, as you can see on the right side, of given dimensions and filled with about 300 cc of the sample of oil for which you would measure the breakdown strength. And there is recommended procedure for increasing the breakdown or increasing the applied voltage, that you cannot increase it suddenly. It has to be increased gradually. It's all specified. And when you measure, in case of weakly non-uniform field, if you, sorry, I'll talk to you later. So in case of weakly non-uniform field, as we have learned earlier, that if you know the degree of uniformity of the field, you can estimate the breakdown strength, because no partial breakdown phenomenon takes place before the breakdown. So EB peak value is given in the field intensity in peak value. Why? One thing, we must know that whenever a breakdown takes place in any dielectric, it is always at the peak value of the dielectric. You may refer it to RMS value, but the breakdown instant at which it takes place is always at the peak value, because it is applying the maximum field or maximum voltage. Very simple. So EB peak is given is equal to root 2 UB, the root 2 times the RMS value of the applied voltage. UB is a RMS. So root 2 times RMS value of applied voltage divided by eta into D. This is true in case of weakly non-uniform field. And estimated eta factor for these electrodes is 0.97. So you have root 2 UB 0.97, the eta factor, multiplied by, because measurement is recommended to take to take place. The gap setting is recommended 2.5 millimeter. So that gives the EB value in peak value of the applied power frequency voltage to the order of 5.8 UB, where UB is in kV and RMS value. So the electrodes are placed in the container of the given dimensions and filled with the sample, and there is a standard procedure of making at least 6 readings. This is a very common practice all over power system. Wherever oil as an insulating material is used, because oil is still used for providing insulation as well as carrying away the heat generated within transformer. With bulk of oil in very large transformers, it is still very commonly used. And a problem with oil is that the quality of oil deteriorates over the time because of the foreign particles, because of the sludge formation in the oil, aging, you can say. So the oil quality must always be continuously checked, or I mean to say on and off. After a while it must be checked, and if the breakdown strength of oil goes too low, there is a process to regenerate the quality of oil by a centrifuge. I mean, it passes through a centrifuge and the foreign particles, humidity, everything is taken away, and the oil breakdown strength increases. So this is a very common activity in power system, and that is why it has been so well standardized. The procedure to check the quality of oil is very well standardized all over the world. It is done like that. Okay. Yeah. Then the measured electric strength of highly purified mineral oils could be to the tune of 10,000 to 4,000 kV per centimeter. I mean, people, a very highly purified oil in utmost clean and best possible conditions, people have measured the breakdown strength of oil to the order of 1,000 to 4,000 kV per centimeter. But when you measure under the practical conditions, for the commercial oil, you can say it is measured only about 350 kV per centimeter. So the value, what I just spoke, 1,000 to 4,000 kV per centimeter, can be said to be near intrinsic strength value of the mineral oil. Near intrinsic strength value of the mineral oil is of the order of 1,000 to 4,000 kV per centimeter. But the practical strength in commercial oils is never more than 400 kV per centimeter. 350 is a good norm and followed. So see the difference. Many-fold times the actual inherent strength of the oil is many-fold times the practical strength measured. So you have to define always under what conditions you have measured the breakdown strength of oil samples. And it is very difficult to measure extremely high value, as I mentioned, highly purified, but because that requires a lot of efforts So that is not that. That is why the concept of practical breakdown strength has been developed. Now I'll just, for your sake, read out power frequency, AC breakdown voltage, field intensity of transformer oil sample having different moisture content were measured by Hawley. In this diagram, as you see, with increasing temperature, as you can see, with increasing temperature here, this is increasing temperature, and between the same calotte electrode for a gap distance of 2.5 millimeter, and the calottes are forming for this gap distance a weakly non-uniform field of 0.97 eta factor. This can be very easily estimated. And Hawley measured, because the humidity content in oil affects the breakdown strength very severely. So just to give you an idea, you can imagine when the humidity content is only in the topmost curve of the order of 5 ppm, that is 5 parts per million, and you measure at, say, normal temperature of, say, 30 degrees centigrade, you are measuring, can you imagine, the kV per centimeter to the order of more than 300. This is the practical strength, as I was mentioning, of the order of 350 kV per centimeter. But when the humidity content is increasing well, over the time, it does happen that when the transformer is under rain and different weather conditions, it has a the humidity ingress property. Humidity is absorbed by the transformer. Howsoever you may prevent humidity to reach the transformer, it does reach. So when it is of the order of, as you see, 100 ppm and 200 ppm, the same breakdown strength of more than 300 kV per centimeter reduces to something like only 50 kV per centimeter. What a drastic reduction in breakdown strength. And then it is not desirable to continue with the oil under such conditions. They must do something to purify the oil. That means you take away the humidity content and also the other the foreign particles which come up in the transformer because of so many types of electrodes, insulation, and everything being used. There's so many materials. Steel is there, copper is there, so many fibrous materials are, or maybe their press boards are there. So all these may give out some foreign particles, and all these things affect adversely the breakdown strength. So this is an interesting measurement done by Hawley. Yeah. Now we'll shift over to the intrinsic strength of solid dielectrics. In fact, the solid dielectrics have still higher inherent breakdown strength, which is sometimes unbelievable. As you see, I'll talk about the procedure to measure the intrinsic strength of solid dielectrics are given. Okay, we can first talk about that. In order to measure the intrinsic strength, preparation of the test sample is of utmost sensitive part involving considerable amount of precision techniques and efforts. And it is not done on just one sample. It is done on tens of samples, and the measurement is done. And maybe the highest, whatever you are able to get, you may be able to call it to be intrinsic strength. Because every time the breakdown takes place in such samples also, the breakdown value is always dubious. It may not be reflecting the inherent property of the material. Instead, there may be some external cause leading to the breakdown. And to eliminate these external cause which may lead to premature breakdown, you have to prepare the samples. So there, people have done research. Nowadays, it may not be being done so widely, but because we got the information what happens. So there are two types of samples prepared. One, in the literature, when you refer, recessed specimen. On the left side, as you see, this is the recessed specimen. That means a thicker block of the solid material is taken, and it is mechanically the thickness for which you want to measure the breakdown, which is in micrometers, is prepared, is achieved by mechanically taking away the material. And till you get the required thickness, which is in micrometers, because the breakdown strength is very, very high, as you can see on the right side, of the order of 850 kV per millimeter. Even for such a small, on such a small sample, is it possible? If you take 1 millimeter thickness, it's not possible to apply 800 kV. 800 kV is a very, very high voltage. So what do? You prepare almost a uniform field, and you take the thickness of the solid dielectric of the order of micrometers. And then in uniform field, you can convert it directly into millimeter. See, it is also not given in centimeter. Because it is in centimeters, it is very, very high. So this is how the recessed specimen is produced, that you work out the required thickness from a higher thickness block, and then deposit the two electrodes, the high voltage electrode and the low voltage electrode. You deposit with the help of vacuum deposited aluminum electrodes. A vacuum, a kind of a metallic spray arrangement is there under vacuum, so that, why do you take it up? You don't want any micro voids formed between the electrode and the material. The electrode must be in such condition, in such good contact with the solid material, that no micro voids are given rise. So the vacuum deposited aluminum electrodes are people have done it this way for both the electrodes, that is high voltage, and the ground electrode. And the other specimen sample was prepared by McKeown, and he prepared the sample in a slightly different way. It is given on the right side. He has taken polyethylene disc. He's measuring the breakdown strength of polyethylene sheet, of micrometer thickness, and it is placed between the two perspex disc, and on both sides the 9 mm dia steel spheres, very smooth steel spheres, 9 mm dia, very small. You can imagine this total size of the sample, about, say 9 mm, about a centimeter diameter spheres are taken. In between the two spheres, the upper sphere is the high voltage electrode, and the lower sphere is the ground electrode. The sample, micrometer thickness sample of polyethylene, is placed, and the gap formed between the sample of the polyethylene and the steel spheres, and on the two sides the perspex discs, is filled with epoxy resin. Epoxy resin is in liquid form, semi-liquid form, you can say, which is filled under vacuum, so that no voids are formed anywhere in the sample, and the epoxy resin then over the time solidifies, so your sample is ready. So when there is a comparison here, as you can read also, the actual thickness of the specimen sample is reduced to about 50 micrometer. 50 micrometer. So 10 to the power minus 6. So you apply, whatever voltage you measure, you multiply by 10 to the power of 6. So you get the voltage, actual voltage, when you want to calculate for per meter. So the values measured here are given in kV per millimeter, the breakdown voltage or electric strength of the specimen. For both the types of specimen, the lower one, the recessed specimen, gave lower value of breakdown strength of the same material, and the upper curve, when measured with McKeown specimen preparation of the sample, gave much higher, to the tune of 850 kV per millimeter. And another thing, the breakdown strength has been measured with increasing temperature. When the temperature increases, it affects adversely the strength of the solid dielectric. And as you can see, the lower breakdown strength is measured at higher temperatures, to the tune of, say, 80 degrees centigrade. So when it is normal temperature of the order of, say, 20-25 ambient temperature, the breakdown strength of the order of 850 kV per millimeter. 850 kV per millimeter. It's a very, very high, unbelievable breakdown strength. So that cannot be measured so in a simple fashion everywhere. So if you might have read in some literature that the breakdown strength of this solid material is this much, people don't specify under what conditions it has been measured and what type of breakdown strength is it being conveyed. So in fact, to talk about the breakdown strength of solid dielectrics unless you know under what conditions it has been done, it could be misleading. The values could be misleading, because if you have taken care, the values measured could be of this order. Simple polyethylene to the tune of 850 kV per millimeter is unbelievable for some. So misleading figures are available in the literature. Now I think you can uh, understand why those figures should not be actually given. The details should be given under what conditions it has been measured to be. I mean, the field conditions, the voltage, and this is uh, is normally given in kV per millimeter of uh, the peak value. Normally, it should be given in peak value. As I said, because the breakdown always takes place at peak value of the voltage. Hmm? Yeah, let's proceed further. Let me see what is the time left. Yeah, mechanism of breakdown in extremely non-uniform fields. Uh, we have uh, yeah, uh, when we compare the mechanism of breakdown in extreme, what we discussed so far was under the uniform or nearly uniform field conditions. So the breakdown mechanism under the extremely non-uniform field would be certainly different. How different will it be? You know that in extremely non-uniform field conditions, the breakdown always takes place with preceding partial breakdown phenomena. Breakdown directly would not take place in extremely non-uniform field configuration. The breakdown would always take place with uh, preceding partial breakdown phenomena. So that is true in all dielectrics. We discuss so much. The corona is nothing but partial breakdown in extremely non-uniform field. What will happen in case of solid and liquid dielectrics when you measure, when you experiment in extremely non-uniform field? There also partial breakdown would take place. The partial breakdown phenomenon, treeing process, we discussed uh, in the last two lectures. The similar treeing process would also develop in case of liquid dielectrics in extremely non-uniform field. So the mechanism of breakdown is more or less similar in solid dielectrics as in case of gaseous dielectrics in extremely non-uniform field. But the cause and source of charge carriers are different. The charge carriers here are not electrons in solid and liquid. Here they are ions. So the uh, causes and sources of charge carriers are different. The cause of breakdown also may be different. As I said, there is a kind of a field enhancement because of the inclusion of gas, inclusion of foreign particles, etc. So in case of solid dielectrics, a, a weakly non-uniform field is preferred by design. That is why, because in fact, you would have preferred that in even in gaseous dielectrics, but that would have made the size of the installation so big, it is not possible. So when you use open air, atmospheric air, that is not taken into consideration. But certainly when you use the enclosed chamber, SF6 gas, GIS, etc., you do try or you do attempt to remain within weakly non-uniform field conditions. But the pre-breakdown process generally begins at an extreme intensity or distortion of local field at the so-called weak point, as I just now mentioned, in case of solid and liquid dielectrics. Weak points adversely affect too much in case of solids and liquids. And under the action of these high local electric field, that is field enhancement, the solid and liquid dielectrics may either lose the electrical insulating property locally, leading to partial or complete disintegration of the material. Because when the partial breakdown in solid and liquid take place, they degenerate the material very highly. At field intensities closer to breakdown, massive space charge formation, because you always know when the partial breakdown activity is there will be space charge formation. What is space charge? Is the concentration of like polarity charge. So space charge injection into the dielectric takes place by the electrodes, causing considerable increase in electric stress in the dielectric. I mean, there's the space charge injection by the applied field intensity would take place, and that causes again distortion in the electric field or enhancement of electric stress locally. Development of electrochemical forces, we haven't talked about it because of the space charge injection by the electrode having high voltage. The injection process of the space charge, or the you can say the charged particles, is so much accelerated within the liquid dielectrics that it produces kind of a movement of the liquid, and that leads to electrochemical forces within the dielectric. And there is another field which you can read in literature, in my other books, which is called EHD, or electrohydrodynamic. That means the dynamic forces produced within the dielectric which make a turbulence in the liquid dielectrics. And how do they affect the breakdown? Such developments affect the breakdown strength adversely to a very great extent. This is especially true in liquid dielectrics because there is movement of the liquid there, and movement may not necessarily affect adversely because of the movement, healthy liquid dielectric may replace the one which has been adversely affected by the charge injection. So these are fields of research you can take into consideration later. As I was talking, these two, I love these two photographs. So on the left side is development of typical tree in transformer oil, mind it. And on the right side, that has been taken by Torshin, Dr. Torshin, and on the right side, a bush type tree in piacral, the solid material, is shown here. This was taken by a colleague of mine, Pilling, Dr. Pilling, and you see the similarity in liquid and in solid, in extremely non-uniform field. The tree formation in the liquid, it is not permanent because it will be replaced by the oil, whereas in the solid, it will be a permanent feature because the conductive channels The tree is nothing but formation of conductive channels. And the conductive channels formed in the liquid, because of the replacement of the liquid, will not be permanent, whereas the conductive channels formed, we have seen earlier also in the blocks of solid dielectrics, how permanent channels are formed in solid dielectrics. So these are that reflects well, if I'm not mistaken, the breakdown in extremely non-uniform fields in liquid and solid dielectrics. When these conductive channels extend to the opposite electrode, it will lead to the complete breakdown. So with this, we can summarize the chapter 6 of the breakdown in solid and liquid dielectrics. I would request you to please read this yourself. So I can quickly read about it so that you also pay an attention. Besides the electrical insulation, solid insulating materials provide mechanical support as a base for the live conductors carrying high voltage. Not just electrical insulation, the solid also provide a mechanical support to the live conductors. Just like you can say in the case of insulator string in the transmission lines, that is providing both electrical insulation as well as mechanical support. The role of liquid dielectrics is basically to fill the porosity in the solid insulating materials and also conduct heat generated in the conductors due to I square R losses towards the atmosphere by their movement. By the movement of oil, heat is transported from the windings to the outside atmospheric to the atmosphere. And this is being also now, it is replaced when gas-filled transformers are used. There is no oil in it. The gas does the same job as the oil. The knowledge of electric field dependent performance in insulating materials helps in designing a more economic, dependable, and reliable insulation system in an apparatus. So, if you have learned about the performance behavior of the insulating materials, you can use it in a better way and more economical way also. The product cost, you may be able to bring it down. How does it behave under different field conditions, under different atmospheric conditions, etc. And unlike in the case of gaseous dielectrics, partial breakdown in solid dielectrics cause permanent damage to the insulation system, which could lead to permanent premature breakdown. When there is a permanent damage, conducting path, treeing process, it may lead to premature breakdown and the gadget may get totally spoiled. It will cause a permanent damage to the apparatus. Although the intrinsic strength of solid and liquid dielectrics is found to be very high, in case of solids, it is very, very high. The researchers have concluded that, as we discussed today, their practical breakdown strengths are much lower. In fact, what interests us as a user or when we are producing an equipment, it is not the intrinsic strength which would interest us so much. The practical, because we are developing the equipment under practical conditions. So the practical breakdown strengths are much lower and of more importance for us to develop the apparatus. And with the development in material manufacture technology, methods of application of insulating materials and equipment production techniques, the in-service maximum electric field intensity in high voltage apparatus equipment could be increased four folds in the it could be increased four folds in the past 5 decades. I'm talking about this, for example, the electric field intensity in power cables. It was less than 4 kV per millimeter, something like 40 years back, 4 kV per millimeter. It has gone to some more than 15 kV per millimeter today in very high voltage power cables. The maximum field intensity at which the insulating material, polyethylene, particularly XLPE, cross-linked polyethylene, work today is more than 15 kV per millimeter, which was almost 1/4 40 years back. How could we produce apparatus with such high field intensities? Only with the knowledge of their behavior, their performance, and the technology to produce the apparatus. So, in this chapter, classification of dielectric properties of solid and liquid dielectrics have been presented, and partial breakdown and breakdown mechanism in solid and liquid dielectrics are also discussed. So we close this chapter number 6 of solid and liquid insulating materials. Then we will go next to the generation of test voltages in laboratories. We'll talk about it in our next lectures. So thank you very much. These are some references. If you want ever to refer, you are most welcome to refer these books. They are available in the market, and you will enjoy reading it. Thank you very much. See you again.